Um, so today we're going to be starting basically the second half of chapter 4, which we'll finish by the end of this week. So if you recall kind of the progression we're in, we're talking about mainly covalent bonding in chapter 4, and we're going to get more details about that today. First, I have the sort of weekly reminder about study habits and things of that sort, the Try Hard Tuesday, as I call it. One thing that's always interesting to look at in this course, as we're trying to build good habits, is when people are actually doing the homework assignments, given that they're open for more than a week. What part of that time period are they actually completing? Now, the downside of our switch to WebAssign is that it's not super straightforward for me to track when you guys are actually doing the homework. Not to mention, since the homework assignments aren't timed, when you open it up and when you start it, when you finish it, it's kind of in some ways irrelevant because you could have it just open sitting there idly and there's no problem with that. I still have reason to believe that most of the effort on the homework assignments occurs on the very last day that it's due. If you're not in that boat, good job. But I have suspicions about that for most of you, mainly because about 90% of the emails that I get about the homework assignment are on the day that it's due. So that's a little bit anecdotal, but it seems to be the case. Just to remind you then, since I can't actually say when you're doing the homework, although again, it's probably last minute for many of you, there are a lot of advantages of starting it earlier in the week. Again, it's untimed, especially the homework assignment part. The quiz is timed, but the homework assignment is untimed. You have 4 attempts at each question. There's only a small deduction if you don't get it right the first time. So it's helpful to do it throughout the week because then as difficult problems come up, you can get help on those from me or from a tutor or whatever you think is the best situation for you. And then as you get towards the end of the week and you want to finish up that homework assignment and take the quiz, you can sort of test yourself to see, did I actually learn this? As opposed to if you wait to the last minute, you kind of just have to rush through it. You don't really have time to really test yourself and check yourself like that. There is the possibility of if you're trying to cram both assignments, especially in the same day at the very last minute, you'll kind of burn out and not perform your best towards the end, especially. And I think just in general for this course and for most college courses you'll take, it's better to spread out your effort and do a little bit every day. If you're kind of the feast or famine mentality that worked in high school of I'm going to forget about this course until 2 hours before the exam, doesn't usually work in college, as you may have already figured out. And doing the homework assignments throughout the week and trying to take them seriously like this is really one of the best ways in this course to do that. So that's my suggestion to you. Don't wait till the last minute. Get your help throughout the week when you need it. And hopefully by the end of the week, then you'll be very up to speed and clear on everything that was covered in that assignment. All right. The stuff that we're covering today, I think it's at least some of it will probably be in the upcoming assignment. So, but anyway, what we're doing in this part of the course is we're talking in more detail about covalently bonded compounds. So we started with VSEPR in this chapter, which was the topic that allows us to predict the shapes of molecules, and from that we can determine whether or not they're polar. But the topic for the rest of this is going to be different theories, different models of how orbitals overlap to form covalent bonds. So we have the basic idea that when you form a covalent bond, you are sharing 2 electrons between 2 atoms. But how exactly do the orbitals get involved in that? Because we know from chapter 2 that all atoms have their electrons arranged into different orbitals in increasing order of energy. But then what happens to those orbitals when 2 atoms come together and make a bond where they're sharing 2 electrons? So that's what this is going to talk about. So for very simple molecules, diatomics especially, which I'm going to show here, we can sort of rationalize the formation of covalent bonds as just the overlap of 2 atomic orbitals. Now, this is not entirely true, but it's a convenient and easy picture to start with, and it was a way that a lot of people thought about bonding for a long time. So if we have H2, the simplest diatomic molecule you can have, so hydrogen is the first atom on the periodic table, first element on the periodic table, and so we know that its electron configuration is just 1s1. It has a single electron in a 1s orbital. So if we have a hydrogen atom, it's going to have a spherical 1 orbital with 1 electron in it. And if we want to bond that to another hydrogen atom, an easy way to think about this happening is just that a second hydrogen atom, identical in all ways, combines with it. And then what's going to happen to make the bond is that these 2 spherical 1s orbitals are going to overlap with each other. And the two electrons that then make up the bond are going to be in the region where those two orbitals are overlapping. Again, from a sort of pictorial standpoint, this is satisfying, although it's not entirely true, as we'll see later on, how things actually work. But you're going to get sort of a picture like this. Two overlapping 1s orbitals. So there's the nucleus from one, the nucleus from the other. In that overlap region, you're going to have both electrons now paired with opposite spins. So again, this sort of what's called a localized bonding approach that we'll start with assumes that you're going to just have intact atomic orbitals, in this case, one from each atom, that overlap with each other to make a bond. So the atomic orbitals are still there, they're just overlapping with each other. Now, we can also do this with other types of valence orbitals. So a key point in all of this that I want to emphasize at the very beginning is that whatever bonding theory we're using, this simple one that we're starting with, the more complicated one that we'll get to towards the end and next lecture, it's always going to be the valence electrons that are involved. So we talked about the valence electrons being those outermost electrons that are in the highest principal quantum number, and those are going to be the ones that overlap and make bonds with each other. So if we go to a more complicated one, chlorine, the electron configuration for chlorine from the periodic table, the previous noble gas is neon. Those are the core electrons. And then in the valence, we're going to have, it's a group 7, so we're going to have, sorry, 3s in this case, 3s2, 3p5. So each chlorine atom is going to have a filled 3s orbital in the valence shell, as well as 3p5, which is just all but one of the p orbitals filled. So what you're going to have, because the s orbitals are filled, we can't overlap those to make a bond, because you can still only put 2 electrons into that overlap region. That's what this bonding theory sort of assumes, that everything's going to just pair up like that. So we can't overlap the 3s orbitals because they're filled. So we're going to use an unpaired electron in the 3p orbital instead. All right, because as we said, this is 3p5 configuration, which means there's going to be one p orbital that's singly occupied, that just has one electron in it. And so if you have one of those on each chlorine atom, and you arrange the two p orbitals pointing towards each other, so you have a 3p orbital on one chlorine atom that's singly occupied. Remember, the p orbitals have this sort of dumbbell shape to them. So there's 3 of them, px, py, and pz. This would be one of those 3. And then you take another one that also has a single electron in it from a second chlorine atom. Again, what we can do in this localized bonding approach is just overlap these two p orbitals and have the 2 shared electrons be in that region where they overlap with each other. So this is a little bit harder for me to draw, but I'll try my best. You're going to have a p orbital. You're going to overlap it with another p orbital. And in that overlap region, you're going to have the 2 electrons. I did not do a perfect job with that. Let's try that again. All right, so that's going to be the overlapped p orbitals with the electrons shared in between them. Again, we're still assuming that the atomic p orbitals are intact. They're just overlapping with each other to allow that bond to be formed. And then you can do it with 2 different atoms as well. So it doesn't have to be 2 of the same, as long as they each have an unpaired electron that they can share. So hydrogen is 1s1, as we said. Chlorine has a valence configuration of 3s2, 3p5. So each of them has an unpaired electron that they can share, but one of them is in an s orbital from hydrogen. The one that we said from chlorine is in the p orbital, like we just talked about. So you can also have 2 different orbitals overlapping as well. So you'd have a hydrogen 1s, and then a chlorine 3p. These can overlap with each other to make bonds between 2 different atoms, involving 2 different orbitals as well. So you'd have your hydrogen 1s orbital, your chlorine 3p orbital. Not really drawn to scale here. The 1s should be a lot smaller than the 3p, but you get the idea that they overlap with each other. The 2 electrons are going to be shared in that portion where they overlap. And that's going to make HCl with the 1s from hydrogen and the 3p from chlorine overlapping. So this is called the sort of localized or valence bond approach to covalent bonding. It's assuming that you have atomic orbitals that can overlap with each other and electrons get shared where those 2 are overlapping. Now, the problem, though, is that this doesn't really explain what happens in many other types of molecules. So this is fine for just 2 atoms coming together to make a bond, But what if we had a more complicated structure like the type we talked about in VSEPR, an AX2 or an AX3 or an AX4, more electron groups that are coming together around the central atom? How are those going to be bonded together? Because the problem we run into is that if we're just going to use valence s and p orbitals to do this, remember the s orbital is spherical, so I guess in theory it can bond in all directions because it's spherical. But the p orbitals, remember, they're going to be aligned in the x, y, and z directions. So the p orbitals are 90 degrees apart from one another. One's in the x direction, one's y, one's z. So if we're going to use just plain old p orbitals to make bonds with our central atom, we're going to be restricted to 90-degree bond angles. And we know that most of the structures that we talked about in VSEPR don't have 90-degree angles. You have 180 degrees if you're AX2, you have 120 if you're AX3, you have 109.5 if you're AX4. So how do we rationalize that if we're just using p orbitals that are all 90 degrees apart? So the approach that we're going to take, the next theory we're going to talk about, is called hybridization. It's also part of this valence bond method that involves localized orbitals, but it's the idea that the orbitals on the central atom are going to mix with each other. The valence orbitals that are available in the central atom are going to mix with each other to make new orbitals that are oriented in the right way to make these different shapes. Now we're going to go through sort of the theory of this method, how it works, in as much detail as I have time for today. The most important thing you're going to have to be able to do, and we'll get to that later on after we get through all the theory part, is just predict what is the type of hybridization at the central atom. So that's going to be what's coming towards the end, but we want to understand a little bit how this works too. Okay, so if we go to the first type of hybridization we're going to talk about is SP. I dropped one of my sheets. Where did it go? Yeah. All right, so SP hybridization, what you're going to find is that each of these different types of hybridization correlates with one of the electron group arrangements that we have. So we talked about the 5 electron group arrangements last time: linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, octahedral. And then each one of those is going to have a hybridization associated with it, which describes how the orbitals on the central atom mix with each other to make those bonds. So SP hybridization corresponds to the linear geometry. So it's going to occur when we have 2 electron groups bonded to our central atom. And the way that hybridization sort of works, if we look at the valence orbitals, an example would be beryllium chloride, BeCl2. I guess technically an ionic compound, but we can sort of rationalize its structure in this way. So for beryllium chloride, the valence orbitals are going to be 2s and 2p. So 2s orbitals are lower in energy than 2p. And the configuration for beryllium ends with 2s2. It's in the second column of the periodic table. And so again, if we just took the atomic orbitals as our starting point, it would be hard to rationalize how does this central atom beryllium make 2 bonds that are 180 degrees apart. You just have a filled s orbital. How does that work with making? So the way that it works then is we do what's called hybridization. So we're going to hybridize 2 orbitals in this case. If we want to have 2 electron groups around our central atom, we need to hybridize 2 orbitals. So we're going to take the s orbital and one of the p orbitals. So we're going to mix 2 orbitals together. And then what you're going to form are going to be a set of hybrid orbitals here that are labeled as SP, that are intermediate in energy between the two. So you're mixing a lower energy s orbital with a higher energy p orbital. So the hybrid orbitals that form are kind of in between in that energy. And then that leaves still 2 other 2p orbitals that are unaffected. All right, so again, the energy of these sp hybrids is in between s and p, because these hybrid orbitals really are a mixture of an s and a p orbital. It's not a pure s orbital anymore. It's not a pure p orbital anymore. It's an s and a p mixing together, and there's 2 of them now because you're mixing one s and one p to make 2 hybrid orbitals. And 2 of the 2p orbitals then are unchanged. They're not involved in this mixing for this case. So then what happens is after we hybridize the orbital, these 2 valence electrons that we have in beryllium, they end up in this set of hybrid sp orbitals. Now they're at the same energy. Now they're each unpaired, and that then allows us to make 2 identical bonds that end up being 180 degrees apart. So when we make the 2 bonds in beryllium chloride about that central atom, we're not using s or p orbitals. We're using these hybrid sp orbitals. So then the way that it looks in a more pictorial sense is you're going to basically make 2 identical orbitals that are 180 degrees apart. They look kind of like in between s and p orbitals. So all the hybrid orbitals kind of look like this. I guess this one's a little bit more like an S, so it's probably, yeah, probably more like that. It's fine. So it has sort of a mixed character between S and P. You have two of those orbitals that point out 180 degrees from each other, and they overlap with the outer atoms. Again, the theory is a little bit complicated. It's not super important that you fully understand it, but I want to give you the background to kind of see how this works. Now, the next type we're going to talk about, which is for 3 electron groups, is called sp2. So this is going to be when your geometry is your trigonal planar geometry. We're going to ignore lone pairs for now, but even if there were lone pairs involved, you would still use the same approach. So trigonal planar geometry, this would work for AX3. So an example of this is going to be BF3, boron trifluoride. So boron is in the 2p block of the periodic table. So it's right next to beryllium, the one we just did. So the valence electron configuration for boron is going to use the 2s and 2p orbitals. 2s orbital lower in energy than 2p. And the configuration would be 2s2, 2p1 for those valence electrons. That's straight off the periodic table. So that's going to be the central atom boron here. Okay. Now, again, if you're trying to rationalize how does this make 3 bonds, BF3 has 3 bonds, they're 120 degrees apart based on the geometry that we would predict, how would this arrangement result in 3 identical bonds 120 degrees apart? Because you have 2 electrons that are paired in the s orbitals, only 1 unpaired electron, and it's in a p orbital. So the way we do this, again, is we mix orbitals together. So we're going to take our s orbital, and we're going to mix it now with 2 2p orbitals. So we're going to mix 3 orbitals together. Again, we call that process hybridization. So we're going to hybridize the 2s orbital and 2 of the 2p orbitals. Okay. So what that does is we're taking 3 orbitals and mixing them together, and we're getting 3 identical hybrid orbitals that we're going to call, in this case, sp2. And again, if it's not obvious, the naming that we use, sp2, is because we have 1 s orbital mixing with 2p orbitals to make these hybrids. So there's going to be 3 of those orbitals, and they're labeled as sp2. That leaves 1 of our 2p orbitals unaffected, so there's going to still be 1 additional 2p orbitals. Whenever we do any of these bonding approaches that we're talking about in this course, or anyone that you'll see in chemistry, you don't create or destroy orbitals. So we're starting with 4 valence orbitals on the central atom. We're mixing together 3 of them to make new valence orbitals, but there's still a total of 4 valence orbitals present. We don't lose or gain any. All right. And now, because we have this arrangement, our 3 valence electrons from boron are going to go into each of these orbitals to follow Hund's rule. And now you're going to have 3 identical orbitals with unpaired electrons available to overlap with the outer atoms and form those 3 identical bonds. All right. Again, what we're working towards, and this is going to be the subject of the majority of your assessment questions, is going to be, for the molecule BF3, what is the hybridization of the central atom? So we'll talk about a simple way to do that later on. But sp2 would be the hybridization that corresponds to that. And this is kind of the way that the orbitals would arrange themselves in that situation. All right, the last one we're going to give a lot of detail on is sp3. There's only a few more to consider. This is the last one we're going to talk about a lot. So then what we'll have here for sp3 is this is going to correspond to the tetrahedral geometry. So if we have tetrahedral geometry, that means there's 4 bonds to the central atom, 4 electron groups around it. And so the pattern continues. We're going to end up hybridizing 4 orbitals. So a classic case of sp3 hybridization is anytime carbon has 4 single bonds, so methane, CH4 being a simple example of that. So we have 2s and 2p orbitals on carbon. This is our central atom that we're focusing on for this. And so then for carbon, the configuration is just 1 over from boron. We're just continuing down the line. 2s2, 2p2 for the valence electrons. And again, just looking at this configuration, it's hard to rationalize the formation of 4 bonds in a tetrahedral arrangement because you only have 2 unpaired electrons, and they're in 2 different 2p orbitals that have to be 90 degrees apart from each other. So there's just no easy way to rationalize this making a tetrahedral unless we hybridize these orbitals. And so what we're going to end up doing for sp3 hybridization, as the name implies, is we're going to hybridize all four of the orbitals. All three of the 2p orbitals, the 2s orbital, we're going to mix all four of these together. And we're going to make a set of identical sp3 hybrid orbitals that are 109.5 degrees apart, arranged in a tetrahedral orientation. So that gives us four orbitals, all equal energy, and we don't have any unhybridized orbitals left because we've used all of our valence orbitals to make these hybrids. And so now the four valence electrons that carbon has are going to go one into each of those orbitals. That allows us to form the four bonds by overlapping with the atomic orbitals from hydrogen that it would provide. Okay, so again, hybridization is focused on the central atom primarily for most of the things we're going to do with it. And you're going to make hybrid orbitals on the central atom. You're going to overlap those with either other hybrid orbitals that are on the outer atoms or just atomic orbitals in the case of hydrogen, where it just has the 1s available. All right, so that's how hybridization works for the first three cases. We're not going to go into detail into the other two for now. We're going to just move on to a summary of this. So this is going to be sort of the key summary table that you'll need. And again, the most of things you're going to be able to do is going to be looking at a Lewis structure that you've drawn, which we now know how to use to predict the geometry. And also we can use that same Lewis structure to predict the hybridization of the central atom. And predicting hybridization is all about what we call the steric number, which is also known as just the total number of electron groups on the central atom. So that's sort of how lone pairs get involved. A lone pair counts as one electron group, and anything bonded to the central atom counts as one electron group. The total number of those, which dictates the electron group arrangement, also dictates the hybridization. And it's very simple to do. So we just have these five possibilities, as we talked about, 2, 3, 4, 5, or 6 electron groups. And from the way we predict the hybridization is as follows. So if we have 2 electron groups around the central atom, steric number of 2, we need to hybridize 2 orbitals to accommodate that. So we pick the first 2 in this list. So we have an s orbital available. We have 3 p orbitals available. As we'll see, some of the d orbitals can get available as well in some cases when you go beyond 8 electrons. But we're going to just need to hybridize the first 2 if we have 2 electron groups, which gives us sp hybridization. And that corresponds to a linear arrangement of those electron groups. If we have 3 electron groups, we need to hybridize the first 3 of these orbitals. So the s orbital is going to hybridize with 2 of the p orbitals to give us a total of 3 hybrid orbitals that we call sp2. And that corresponds to the trigonal planar arrangement. For 4 electron groups, we need to hybridize 4 orbitals. So we take the first 4 in this list, 1s and all 3 p orbitals, as we just talked about. That gives us sp3 tetrahedral arrangement. And then finally, the ones that we haven't talked about in detail, but we're going to still consider at times in this course are, we discussed the possibility in when we introduced Lewis structures about going where you have more than 8 electrons around the central atom, exceeding the octet, which is possible if you're in the third row of the periodic table or below. And so when that happens, then we have to use more than 4 hybrid orbitals because we're going to have 5 or 6 electron groups that we're accommodating. And those correspond then to the trigonal bipyramidal and octahedral geometries that we also recently talked about. So if you have 5 electron groups, you need to hybridize 5 orbitals. You only have 4 available from the s and p, so that's where we sort of invoke dipping into these d orbitals and including one of those to give a total of 5 orbitals, which we label as sp3d. You may also see it as dsp3. Don't worry too much about the order that those come in, but sp3d is the more common way of writing it. And again, it requires us to hybridize 5 orbitals, these 4, but then we have to also get one d orbital involved to have 5 electron groups. And that corresponds to the trigonal bipyramidal arrangement. And then the last case, the highest number we'll go to is 6 electron groups. So we need to hybridize 6 orbitals, 1, 2, 3, 4, 5, 6, which we call sp3d2. And that corresponds to the octahedral electron group arrangement. So I don't know if that's thunder or if they're bowling in the HVAC again. All right, so we have, this is sort of, again, the key summary table. the key thing you're going to have to be able to do on homework assignments and exams. If you draw the Lewis structure out, you can use that to predict the VSEPR structure, as we discussed last time. And with the correct number of electron groups around the center atom, you can also predict the hybridization. Now, I don't have a separate slide on this, so I want to make sure I also emphasize that lone pairs count when we're counting the number of electron groups. So remember that when we count the number of electron groups around the center atom, that's going to include any atom that's bonded to that center atom, plus any non-bonding or lone pair electrons that are on that center atom as well. And so those are going to involve hybrid orbitals also. So the hybrid orbitals in a molecule at the center atom are going to be involved in forming the bonds to the outer atoms. And if there's any lone pairs on the center atom, those are also going to be included in one of those hybrid orbitals. So maybe as a quick example, if you have an AX3 geometry, AX3E, for example, ammonia, NH3, we know that this should have a lone pair on the central atom and 3 bonds to hydrogen. So that nitrogen is going to have a total of 4 electron groups because it has 3 bonds to the hydrogen atoms and a lone pair. So that's a total of 4 groups. So this one should be sp3 hybridized. Again, we don't just count the number of atoms bound into the central atom. We also have to count lone pairs in that total. So there's a total of 4 electron groups. 1, 2, 3, 4 gives us sp3. And then what would happen is 3 of those sp3 orbitals are going to form the bonds with the 3 hydrogen atoms by overlapping with hydrogen 1s orbitals. That 4th sp3 orbital is going to house the lone pair that's also on the center atom. Okay, so lone pairs are also going to be in those hybrid orbitals when you have that situation arising. All right, let's do some examples then of just applying this approach. So just like we saw for VSEPR, predicting hybridization requires you to draw a reasonably correct Lewis structure. It's still not that important that you get, the number of double bonds and all that stuff exactly correct in most cases, but you have to have the right number of electron groups around the center atom, just like you do for VSEPR. So if we have COCl2, it's called thionyl chloride, and carbon is the center atom here. We want to know what is the hybridization. So again, this all comes from a Lewis structure, so let's quickly review that. I'm not going to do all of these in great detail, but we have carbon, oxygen, and 2 chlorines in the structure. We need to count the number of valence electrons, so we need our periodic table to do that. And so what we'll have then is carbon is in group 4, so it has 4 valence electrons. We've seen that one today. Oxygen is 2 over, it's in group 6, so that oxygen is going to have 6 valence electrons, and then we have 2 chlorines from group 7 that are each going to have 7. So group 4, group 6, group 7 are the 3 elements that are involved in this structure. 1 carbon has 4 valence electrons. 1 oxygen that has 6 valence electrons. And then 2 chlorines, Cl2, that each have 7. So this is going to have a total of 24 electrons. So as is typically the case when carbon is the center atom, we don't have any lone pairs on the center atom. This is a multiple of 8, so that means there's not going to be any lone pairs left over. But let's still verify that and draw the structure. So what we get for this one, if we start with single bonds to the outer atoms, we complete the octets of the outer atoms. So that ends up using up all 24 of our electrons. We have 3 complete octets for 24. That's the number that we have. Now, if we actually stopped here, the structure is not quite correct. So if we were asking you to draw the Lewis structure of the molecule, this would not be a fully correct structure. But we could use it still to predict the geometry and the hybridization. Because again, for those, we don't really care too much about whether we have the correct number of double bonds and things. We know there's no lone pairs on the center atom. That's the critical part. Now, we do need to fix this though a little bit, because right now our carbon only has 6 valence electrons around it, and it should have 8 once it completes its octet. This oxygen atom here ends up having a -1 formal charge, so that's going to be the place where we're going to draw the double bond. We're going to take off a lone pair from oxygen, and oops, don't want to erase the whole thing. Get rid of that last dot. Come on. And then we're going to make a double bond there. So that's going to be the best way to draw this Lewis structure. But even if we had skipped that last step there, we would predict that this is an AX3 structure. Carbon is bonded to 3 atoms, but it has no lone pairs of its own. So that means that term that we like, steric number, is equal to 3. So this would predict a trigonal planar arrangement, but this question asks about hybridization. So carbon has an s orbital and 3 p orbitals available for hybridization. We need to use 3 of those because there's 3 electron groups. So that gives us sp2 hybridization. Okay. So that's what most of the questions on the homework assignment are going to involve. It's just, here's a molecule, get the Lewis structure, predict the hybridization of the central atom. Knowing the details about hybridization, just a little bit of that, a little bit about what hybrid orbitals look like, but mostly it's just predicting hybridization. Now, the other thing that we will sometimes see are going to be some slightly more complicated examples like this, where this is a larger organic molecule. Molecules that contain a lot of carbon, hydrogen, and oxygen are typically classified as organic molecules. It has nothing to do with what kind of farm they're grown on. It's just a classification we use in chemistry. And we want to, for these types of problems, it says complete the Lewis structure and predict the hybridization of all of the carbon atoms in the following molecule. All right. So this is the part that's a little bit challenging for us to do because we haven't really seen something like this yet, and it's going to start coming up now in this chapter. So if you see a problem like this, first of all, your first thought is like, oh, I have to complete the Lewis structure, which means I have to count how many valence electrons there are and distribute them around. That's going to be very difficult if I have this many atoms. But there is a shortcut that I want you to be able to take that works for this. So the first thing to do is, if you see a structure like this, there's going to be some patterns involved. So these types of structures, as we said, they're going to typically have hydrogen in them. And then they're going to have some combination usually of carbon, oxygen, nitrogen, and then sometimes, not very often, you'll see halogens. So X, we call them X, chlorine, chlorine, bromine, iodine. So we're typically going to be giving you problems that would have this combination of atoms in them. And although there are rare exceptions to this, I don't want to say this is like the 100% absolute truth. A pattern that you're going to follow in almost every case is going to be shown here. So the first thing is, if you're looking at a structure like this and trying to fill in the missing lone pairs and missing double bonds and triple bonds that might be there, recognize, of course, that hydrogen is always going to just have one bond. So in reality, you're not going to do anything with hydrogen because hydrogen is going to be shown as singly bonded to either carbon, oxygen, or nitrogen. That's all you ever do with hydrogen. Never have a double bond on hydrogen, never have a lone pair on hydrogen. You stop there. So that one's the easy one. For the rest of these, the p block elements that would be involved, which again are, let me put them in the more logical order. Let's do the order they appear on the periodic table: carbon, nitrogen, oxygen, and then the halogens X. So these atoms, when they're in typical structures like this, they're always going to want to have a complete octet, exactly 8 electrons around them. Okay, so there's really no exceptions to that. What differs between them is the combination of bonds and lone pairs they typically use to achieve those 8 electrons. So for carbon, what we're going to typically have is it's going to form 4 bonds. 4 bonds is already 8 electrons, and that means there's going to be no lone pairs on carbon. Now, this pattern basically comes about from you want to complete the octet and you want to minimize the formal charge on the atoms. And so in order to do that for carbon, it would have 4 bonds but 0 lone pairs. For nitrogen, still a total of 8 valence electrons, but now the combination that works best for nitrogen to get rid of formal charge is 3 bonds and 1 lone pair. So we don't have any nitrogens in this example, but if there was a nitrogen in the structure, again, there's some rare exceptions to this, but in 99% of the cases, you would expect nitrogen to have 3 bonds and 1 lone pair. Oxygen should have 2 of each. 2 bonds and 2 lone pairs, still a total of 8 valence electrons, but just a combination different combination that gives us those 8. And then for any of the halogens, which don't appear as often, but certainly could in these structures, they would have 1 bond, a single bond only, and 3 lone pairs. Okay? So that's sort of the pattern that we're going to follow when we want to complete a structure like this. So if we just work down the chain here, we see that this first carbon atom already has 4 bonds. It's bonded to 3 hydrogen atoms and to the carbon next to it. So we stop there because we don't want to add any more than 8 electrons to that carbon. It's perfectly happy with 4 bonds. But if we get to these next 2 carbon atoms here, each of them right now only has 3 bonds. They're each bonded to 1 hydrogen. They're each bonded to 2 carbons next to them, but that's only 3 bonds for each of these 2 carbon atoms here. Carbon wants to have 4 bonds, no lone pairs. So the way that we can fix that is by drawing a double bond between them. Now both those carbon atoms have exactly 4 bonds like they want. We move on to the next carbon atom in the structure. It currently has 4 bonds, 4 single bonds in this case, so it's totally happy. We get to this carbon atom here and to this oxygen that's bonded to. This carbon atom only has 3 bonds, so it wants 1 more. This oxygen only has 1 bond, so it also wants 1 more. So again, we can solve both of those issues by making that a double bond. The oxygen also should have 2 lone pairs to complete its octet. So in the case that we care about lone pairs, which is not always true, but if we wanted to include it in its full level of detail, that oxygen should also have 2 lone pairs. So now the oxygen has 2 bonds, 2 lone pairs, 8 electrons as it would have. And then finally, when we get to these last 2 carbon atoms here, right now each of them only has 2 bonds, one on each side. So this carbon is bonded to 1 carbon on each side. This carbon is bonded to that carbon and 1 hydrogen, but only a total of 2 bonds for each of those. They want to have 4 bonds, they need 2 more. So if there's 1 bond between them and we need 2 more, we just change that to a triple bond. And now both of those carbon atoms have a total of 4 bonds, 1 single bond and then a triple bond that would count as 3 more. So that's how we would finish out that structure. So that's sort of finishing the Lewis structure. And then the question that's often going to be asked is predict the hybridization of all of the carbon atoms in this molecule. So for each carbon atom, we're going to have a hybridization that we predict. Typically, the problems wouldn't ask you to do it for all of them. It would ask you to select one of them or so. But we're going to do it for all of them here to see how this works. So there's 1, 2, 3, 4. There's 7 carbon atoms in the structure, and we're going to predict the hybridization of all 7 of them using what we just learned. So this first one here has 4 electron groups, 4 things bonded to it. So that makes it sp3. This one here has 3 things bonded to it because one of them is double bonded. So we don't care. Remember, we don't count individual bonds. We count how many electron groups are attached to it. So this carbon has 1, 2, 3 things attached to it, which means it should be sp2. Same for the one next to it. This one has 1, 2, 3 things bonded to it. So it's also going to be sp2. This one in the middle here is again bonded to 4 things, 4 single bonds. So whenever you have 4 single bonds on carbon, it has to be sp3 to accommodate those 4 electron groups. This one here, we have only 3 things bonded to it. It's bonded to 2 carbon atoms and 1 oxygen. When there's 3 things bonded, it's going to be sp2 again. And then these last 2 carbon atoms here, each of them is only bonded to 2 things. There's a triple bond between them, but they all have just 2 electron groups attached to them. This one has 2 carbons, 1 on each side. This one has a carbon and a hydrogen. So when you have 2 things bonded to the center atom, you get that sp hybridization. You just need 2 hybrid orbitals involved. So that's how we're going to predict the hybridization for any of the carbon atoms in this structure. You need to know how many things it's bonded to, and then it just correlates directly with the hybridization. And for carbon, you're only going to see these 3 possibilities, sp, sp2, or sp3. There's no other possibility with carbon because we can't go beyond 8 electrons, which is the only time you would see the d orbitals involved. All right, any questions on that so far? Now, one thing I want to point out before we completely move on from this, it can be a cause of confusion, so I hope that's not the case, but I just want to make sure I'm always telling you guys the full truth. For these examples here where we have sp3d, sp3d2 involving the d orbitals, from our standpoint, that's the prediction we would make. If you see a structure that has 5 electron groups, you would predict that it's sp3. If you see a structure that has 6 electron groups, you would see it as sp3d2. Now, the reality is that's not 100% true. We don't actually really see the d orbitals getting involved in most of these kinds of compounds. So if you have something like sulfur as your center atom, you can have 5 or 6 electron groups around sulfur, but the d orbitals are not actually involved in that. So that's just to sort of give you an idea that sometimes things are more complicated than we would initially present in a general chemistry course. But this idea of hybridization is still convenient to use. It's still valuable in a lot of contexts. And the other thing that you should always realize is that in any field of science, when we describe something as a model, which is what these sort of bonding pictures are, this is one model of bonding. One definition of a model that I've seen that I really like is a model is a lie that we tell to help us understand the truth. So that's kind of what we're getting at here, is that there's some things that are not quite right about this, but it's still a convenient way of describing and rationalizing how we get these different structures. So from our standpoint, sure, we can assume that the d orbitals are involved. If you go to more advanced chemistry courses later on, you'll learn that that's not quite correct, and I don't want you guys to think that I was lying to you willfully. It's just part of the way general chemistry is situated in many cases. All right. So the next thing we have to talk about along these same lines are the different types of bonds that can form. So when we have atoms bonded to each other, we know that there's going to be two orbitals overlapping. We know that there's going to be electrons shared in those orbitals, but there's really two main ways that that can happen. So the first one we're going to talk about are called sigma bonds. This is the Greek letter sigma. So again, in chemistry, whether you like it or not, you have to learn the Greek alphabet. So this is lowercase sigma to describe this type of bond, which is going to involve end-to-end overlap of atomic orbitals. So the types of bonds that we showed in the very first slide today that involve just atomic orbitals, those would be classified as sigma bonds. Now they can involve atomic or hybrid orbitals. So when we talk about hybrid orbitals, they can form sigma bonds as well. So when that happens, and we, again, the picture on the first slide kind of illustrates this, the two orbitals come together head to head, they overlap in the middle, and then the two electrons are going to be shared in that region where the two are overlapping, right in between the two nuclei. So when you have a sigma bond, the electron density for that bond, those two shared electrons that are involved, is going to be the greatest in between the nuclei right along the bond. Right along the bond axis. So again, that region right in between the two atoms is where you're going to have the highest electron density. Now, what kinds of orbitals can make these types of sigma bonds? As we said, it can be atomic and or hybrid orbitals are involved. And a key point that I want to make, because when we're talking about hybridization and linking it to this little extension here, if you have hybrid orbitals involved in bonding, they can only make sigma bonds. So there's two types of bonds we're going to discuss. This is the first of those two. This is the only type that can involve hybrid orbitals. So hybrid orbitals can serve two functions. They can either form sigma bonds or they can have lone pairs in them, but they're never going to form the other type of bond that we're going to get to next, which is called pi bonds. So again, the picture that this looks like is exactly what we sort of showed on the first page. So if you have two s orbitals overlapping, for example, in hydrogen, they overlap in the middle, and you have that sort of overlap region corresponds to the sigma bonds, right in between the two nuclei. Once we show the picture of the other one, it'll be more obvious what the difference is. And then if we have, let's say, this is sort of what a hybrid orbital looks like. They're all kind of similar, just different relative sizes of the two lobes. So let's say this is an sp3 hybrid orbital, overlaps with a 1s orbital. They can overlap as well. Electrons would be in there. And again, that sort of density in between the two atoms would be the sigma bond, the one that's right between them. So that's called a sigma bond. And then the other type of bond that can be involved only occurs when you have either double or triple bonds. So single bonds are all sigma bonds. When you have double or triple bonds, you're also going to involve one or more of these pi bonds. So a pi bond is a side-to-side overlap of two atomic orbitals, and it has to be p orbitals from our standpoint. You can make pi bonds with d orbitals as well, but that's not a topic we're going to cover here. So for our purposes, it's a side-to-side overlap of orbitals. It has to be p orbitals. So the definition is more general, but the only type in this course that forms it is p orbitals. And what it does is it results in electron density above and below the bond axis. So the bond axis is basically the line segment between the two atoms, the straight line between the two that are bonded to each other. But for a pi bond, that electron density in that bond is actually going to be above and below where that connecting line would be. So the only types of orbitals that can form pi bonds are unhybridized p orbitals. For our standpoint, again, d orbitals, f orbitals can do it too, but that's beyond the scope of this course. So for the main group molecules we're going to talk about, you have to have unhybridized p orbitals to make pi bonds. So that means you can only have sp or sp2 hybridization, because if your hybridization is sp3 or sp3d or sp3d2, there's no unhybridized p orbitals left. So you have to have one or more unhybridized p orbitals to make pi bonds. So the way that it looks then is we're going to have two p orbitals that have this dumbbell shape. But now instead of overlapping head to head like this to make a sigma bond, they're going to overlap side to side. So you're going to have two p orbitals that are next to each other like this. It's a little bit harder to draw, but you're going to basically have that overlap occurring above and below the bond like that. So it's the side-to-side orbitals overlapping above and below, not in between though like you have for a sigma bond. So that's what a pi bond looks like. Again, these are sort of the details that help us hopefully understand what exactly we're talking about with sigma and pi bonds. The more important thing for this course, similar to what we did with hybridization, is going to be if you have a molecular structure, to be able to predict how many of the bonds in that structure are sigma bonds, how many of them are pi bonds. Knowing what they look like, knowing the orbitals that are involved, that's still important, but most of the questions are going to just go to the level of how many sigma bonds are there, how many pi bonds are there. And so here's how we do that. All right, so if you have, again, this is what's called valence bond theory. That's what we're talking about now. So that's, again, anytime you're using hybridization to make these types of predictions, this is how we would predict how many of each bond there are. So if your structure has single bonds, so most structures do have one or more single bonds in them, then all single bonds are sigma bonds. When we cover the more advanced bonding theory that we're going to just start with a little bit today and continue next time, you will see that it is possible to have a single bond that's a pi bond. But in valence bond theory, which uses hybridization of the central atom as kind of the defining point, if you see a single bond, you will assume that it's a sigma bond. Okay. If we have multiple bonds, so that would be a double bond or a triple bond. We never go higher than that for these types of molecules. Multiple bonds are always going to have one sigma bond. So multiple bond is going to be 2 or 3 pairs of shared electrons. One of those will be a single bond, and the rest would have to be pi bonds. So if you have a double bond order of 2 between 2 atoms, those 2 bonds are going to be 1 sigma bond and 1 pi bond. So again, one of them is sigma, the other is pi. And if you have a triple bond order of 3, the highest that will go to, 1 sigma bond, and now you'd have 2 pi bonds to make up the total of 3 bonds. So anytime you're looking at a structure, for this part of it, to predict the number of sigma and pi bonds, it is important that you have the correct bond order indicated between the atoms, because that's going to determine how many of those bonds might be pi bonds. Every bond is going to involve a sigma bond, whether it's single, double, or triple. But if it's a double bond or a triple bond, you also have to involve pi bonds to rationalize that. So again, the way that that would work is the sigma bond is going to involve a hybrid orbital overlapping with another orbital head-to-head. The pi bonds are going to be unhybridized p orbitals that are perpendicular to that, overlapping above and below where that bond would be. Okay, so then we can do similar analyses here. So this was, I believe, the same molecule that I gave you earlier. Now it's just completely filled in for you. So we saw this structure earlier. We predicted the hybridization of all the carbon atoms. Now it wants to know how many sigma and pi bonds are there. I left out the lone pairs here. There are lone pairs in oxygen, but we're only talking about bonds in this case, which is just two atoms that are bonding together. We don't count lone pairs as being bonds, obviously. So if we're going to count how many sigma and pi bonds there are, we just have to look at all the bonds in the structure, know their bond order, and make sure it's correct, which it is here. We did that earlier. We worked that out, and then count how many are sigma and pi. So again, every single bond in the structure is going to be sigma. So we have sigma here all the way around. All the CH bonds are sigma bonds. All the CC single bonds are sigma bonds as well. So all of those single bonds are sigma. And then when we get to the multiple bonds, remember that for a multiple bond, you have one sigma bond and the rest that make up that bond would be pi. So this first double bond here, we have two bonds. One would be sigma, one would be pi. Carbon oxygen double bond, one is sigma, one is pi. Two bonds, one has to be sigma, the rest is pi. And then for our triple bond here, three bonds, so one is sigma, and then two of them are going to be pi bonds. And you also want to start to link this topic to hybridization. They're not two totally separate things. That's why we're covering them together. So if you recall, this is a review of that last problem we did. Both of these carbon atoms are sp hybridized. And so what they're basically going to have is this carbon atom has two sigma bonds, one to the carbon on the left, one to the carbon on the right. The sp hybrids are going to form those sigma bonds. And then because it's sp hybridized, there's going to be two 2p orbitals that are unhybridized left over. Those are going to form the two pi bonds that are involved in the triple bond as well. So that's kind of the relationship between those two topics. This question didn't ask that level of detail, just wanted us to count. So if I labeled everything correctly and counted correctly, what we should have is a total of 15 sigma bonds in this structure and 4 pi bonds. So there's 19 total bonds, 15 of them are sigma, 4 that are involved in these multiple bonds here are going to be the pi bonds. All right. So any questions on that topic? All right. The last thing we're going to touch on today, the lectures this week might be a little bit on the short side, which I don't think you guys will mind, given this an exam week, and that'll allow us to finish chapter 4 and have a clean break before next week. But we do want to cover one more thing today for the last little time we have left, which is the starting of the more complicated bonding theory that we have. Now, it is a lot more complicated in terms of its, in terms of its mathematics, if we went to that level, in terms of how we visualize things, but we're only going to do it for very simple molecules, diatomic molecules in particular. Is going to be the main focus. So it's going to be more complicated, but it's only going to be done for very simple things, so it's not too bad overall. So the question is, why can't we just use hybridization and valence bond theory and Lewis structures to predict everything? So first, we're going to give you an idea of why we need this new theory to begin with. So if we draw the Lewis structure of O2, oxygen is group 6, so we should have 12 valence electrons, and they would go like this. So we will predict that oxygen has O2 as a double bond, and they're going to be like that. Double bond between the two lone pairs on each oxygen atom. And as we just finished talking about, we will predict that this is a sigma bond and a pi bond. Double bond is one sigma, one pi. Now, most of those predictions are correct, but the problem you run into is one thing that we can predict about molecules from their bonding arrangement is what's called their magnetic properties. So that's going to be a function of, are they attracted by a magnetic field? Are they repelled by a magnetic field? And that's going to be determined by whether or not they have unpaired electrons. Now, when we do valence bond theory, when we draw a Lewis structure and use that to rationalize the structure and the bonding that you might observe, we're going to basically always try to pair up the electrons in that approach, right? We put 2 electrons into each bond. We always draw the non-bonding electrons as lone pairs. So everything is paired up. Whenever you have an even number of electrons, your assumption is going to be, well, none of the electrons are unpaired because you have 2 electrons paired up in each bond, 4 lone pairs total, all paired up together in the same orbital. And so we would predict that this has 0 unpaired electrons. And so if we predict that it has 0 unpaired electrons, we can use that to try to also predict what its magnetic properties would be. And there's really just two key things here. So we will predict that this is what's called diamagnetic. So what diamagnetic means is that it has very weak interactions with a magnetic field, but should be weakly repelled. So if oxygen did indeed have 0 unpaired electrons, we will predict that it's diamagnetic, and that means if we put oxygen into a magnetic field, it should just pretty much just go straight through, or maybe be a little bit repelled, but it wouldn't really have any obvious interaction. Now let's look at what actually happens with oxygen. So that's what this video is going to show here. So what they're going to do is they're going to be pouring liquid oxygen in between the poles of the magnet. And you can see that it sticks in between the two magnets. That's oxygen in liquid form, and it is clearly attracted to the magnetic field. This one's liquid oxygen, but it is the light. It's because it's really faint blue, and there's like a black screen behind it, so you can't tell. If you had like a lot of liquid oxygen, you'd be able to tell that it has a little bit of blue color. This is just not enough of it to easily see that. So there would be a little bit of a blue color if you had a large bath of liquid oxygen. But the important part of this video is that it showed that the oxygen was stuck in between those two magnets because it's attracted to the magnetic field, not repel. Now, this is nitrogen. I mean, that might be exaggerated. I've never pro tip, don't play with liquid oxygen. It's dangerous. So I've never played with it much myself. So I've never seen like that much of it to see how blue it would be. But yeah, it should be blue. But this is oxygen again. It sticks to the magnetic field. Nitrogen, I'll go back a little bit. Nitrogen, as you see, goes straight through. So the woman was pouring nitrogen and went straight through. The guy has oxygen, which again sticks in there. So you can see two different behaviors there. So, but the point of this is that the behavior of oxygen in a magnetic field clearly is of something that would be paramagnetic, which would have unpaired electrons. It's not what we would predict from the Lewis structure. So the reality is that oxygen is paramagnetic. That's the other type of magnetism in its sort of limiting binary forms that we have here, diamagnetic, paramagnetic, which means it's going to be attracted to a magnetic field. And that only occurs if it has unpaired electrons. All right, so clearly this Lewis structure is inadequate at making all the correct predictions. As we'll see later on, it turns out that the bond order is correct. It is a double bond. There's nothing wrong with the number of valence electrons in there. You know, we're not going to turn that on its head. But the arrangement of those valence electrons and the fact that they're all paired up is not actually what's happening. So we won't see until next time how to fully rationalize that for oxygen, because we have to build up to that. That's a slightly more complicated example. But we're going to start today with some of the basics of the last bonding theory we'll cover, which is called molecular orbital theory. Okay. So there's some similarity between molecular orbital theory and what we just did, valence bond theory, but I want to make sure you understand the key difference here. So in valence bond theory, we would take the atomic orbitals on the central atom and mix them with each other to make these new localized hybrid orbitals. What we're doing in molecular orbital theory is we're taking atomic orbitals from one atom and atomic orbitals from another atom and mixing them together to make new orbitals. And those orbitals are delocalized over all the atoms that are involved. They're not just going to be specifically assigned to one atom or the other. They're going to be new orbitals that belong to the whole thing. So that's kind of the key distinction here. So when we mix atomic orbitals together, we take atomic orbitals, or atomic wave functions as they're sometimes called mathematically, and we're going to mathematically combine them via linear combinations. Which means we're going to add or subtract them from each other. But again, the key part of this that's different from valence bond theory is that we're going to form delocalized molecular orbitals. Again, we're not taking orbitals from a single atom, mixing them together and making new localized orbitals that still belong to that atom. We're taking orbitals from two different atoms, mixing them with each other mathematically, and we'll show the pictures of how that looks as well. And that's going to make new orbitals that are delocalized over the entire structure. For what we're doing is mostly going to just be two atoms involved. We're not going to go much more complicated than that. But in even more complicated situations, you would form these new orbitals that are over the entire structure that don't belong to one atom or another, but they belong to the whole molecule. They're covering that whole molecule. Now, what determines which orbitals can mix together? Because as I said, we're going to take orbitals from one atom, orbitals from another atom, mix them together to make new molecular orbitals, they have to be pretty close in energy for that to work. So that means we're going to, again, focus on the valence orbitals, which are relatively close in energy to each other. And it's going to be those valence orbitals that are primarily important for this. The core orbitals are buried, they're close to the nucleus, and so they don't really have that ability to mix with each other as well as the valence orbitals, which are the ones that protrude out the furthest and can interact with other orbitals from the other atoms. So when we do this, we're going to do, as I said, mathematically, it comes from linear combinations, an atomic orbital on one atom, an atomic orbital from another, each described by a mathematical function. Then we're going to either add or subtract those two functions from each other to make the new molecular orbital wave functions. So that gives us then two different types of orbitals that are possible. So the first one is called a bonding orbital, and that's when we add together the two atomic wave functions. So we use Greek letter psi to abbreviate wave functions in general. And a molecular orbital that's bonding is going to have an additive combination of two atomic orbitals. So AO is atomic orbital. We're going to take two of those and add them together for a bonding orbital. The electron density is going to be greater along the bond. Which is, again, between the two nuclei that are involved. And again, there's some similarity of this to the picture we just drew, but it's not two separate orbitals overlapping with the electrons shared between them. It's two separate orbitals combining to make a whole new orbital that's around both atoms, but with the density in between the nuclei holding them together. The energy of the bonding orbitals is going to be lower than that of the atomic orbitals that mix. The other possibility when two atomic orbitals mix together is they can make what's called an anti-binding orbital. We abbreviate those with little asterisks or stars next to them. So we call this one psi star in the sort of wave function nomenclature. And that's going to be when we take two atomic orbitals and subtract them from each other. Again, these are wave functions, so you can think of this as an out-of-phase combination. Bonding is an in-phase combination of the two waves. Anti-bonding is an out-of-phase combination, subtracting them from each other. So in phase, out of phase is sort of the other terminology we sometimes use to describe this. I'll write that here from completion. This is the in-phase combination for bonding. Antibonding is out of phase, and so what an antibonding orbital has is the electron density is greater outside of the two nuclei, outside of the internuclear region, as we call it. And the energy of the antibonding orbital is higher than the atomic orbitals. All right, so we'll draw diagrams of this here in a little bit, but when two atomic orbitals mix together, they form one bonding orbital that's lower in energy than the two orbitals, and they form an antibonding orbital that's higher in energy. If you fill the bonding orbital, you're going to draw those two atoms together and form a bond between them. If you fill the antibonding orbital, you're going to basically cancel that bond, and it's going to push them apart. So it's that's what we're sort of working towards. So the simplest one is going to be we'll start next time with, I guess we are done already. It's faster than I thought. We are going to start next time with how we actually mix specific types of orbitals together, drawing the energy level diagrams that result from that. And again, we'll start with hydrogen, which is the simplest case, work our way up to the P block. That's as complicated as we'll get. So right now, this is, again, just the terminology in the background. We're going to see how to apply it the next class on Thursday.